Okay. So, so in this second part, I'll try to, as well as keep on giving you some very basic results on contact geometry, I'll allow myself to basically inform you about some very powerful theorems. And of course, impossible to give an idea of how they are proven. And I'll also, I warn you that, so I'll give the theorems in a rather incomplete manner because I'll need part of what I'm going to introduce to be more precise about them. But I think it's worth knowing some of the fundamental results in the area. Okay, so existence of contact structures. So, fundamental question that you ask yourself when you study any kind of geometry. Given M manifold, does there exist a contact structure on M? Does it support the contact structure? And also, again, as you may have seen from the previous talk, there's a very close relation between contact and symplectic geometry. So if you know a bit of symplectic geometry and you know that this problem is very hard for symplectic manifolds, you should imagine that it's the same kind of complexity for contact manifolds. But fortunately, the answer, perhaps strikingly so, the answer is positive. I'll basically state the theorem that says that under some reasonable homotopical conditions, any manifold supports a contact structure. So for that, I have to tell you what is the homotopical shadow that we see when we have a contact structure on a manifold. So just introduce a definition. It should be my third definition. Yes, sure. But you can at least read this one. Okay. So the definition is an almost contact structure. It's like very similar to an almost symplectic structure on a symplectic manifold that you possibly saw this morning. So an almost contact structure on a manifold of odd dimension is given by D. Let's assume for simplicity that it's a coorientable hyperplane distribution together with a linear symplectic form on the distribution, sigma, a linear symplectic form on D. And of course, this is the kind of information, the kind of structure that you see whenever you have a contact manifold. So assume this is a coorientable contact structure. So this is the kernel of a global one form. And then D equals to psi and sigma equals to D alpha is exactly an almost contact structure. So if any contact manifold produces for you an almost contact structure, if you were studying the opposite problem, when a given manifold of all dimensions supports a contact structure, you better have one of these guys there, right? So let me also tell you that equivalently, these almost contact structures, you can introduce them using reduction of the structural group of the tangent bundle of your manifold. So again, this reduction of the structural group is simply when you have a tangent manifold, you have the bundle of frames of your manifold, of the tangent bundle. And a reduction means that you can choose nice frames which are invariant with respect to some structure there. So reduction of a structural group to the following. Let me write it 1 plus SPN. This simply means that what you can do is that because you have a coorientable contact structure and you chose a one form alpha, first of all, you can choose a global line field. So this is the one here, this is splitting in the tangent bundle. So you take a global vector field with the condition that its evaluation of alpha equals 1, right? So this is almost always possible because alpha is non-zero. So you choose that vector field. And then, of course, along D or Xi, what you have is this linear symplectic structure. So you can take a symplectic frame, a global symplectic frame there. So that's the reduction here. Moreover, we know that symplectic frames can be reduced to unitary frames using compatible almost complex structures. So moreover, if you put here, so this is a vector bundle with a linear symplectic structure, you can always find a compatible almost complex structure. And this results in a reduction of the structural group to this subgroup. Okay. All right, so here's the theorem. And this is really the theorem in contact geometry. Again, I'll state a very weak version of it. An almost contact manifold admits a contact structure. Now, this theorem has a first part in which M is non-compact. And this proof for a non-compact manifold follows from the work of Gromov. So this is a result of Gromov in the late 60s. So people knew already that when you have a non-compact manifold which supports an almost contact structure, automatically it supports a contact form. Now, the very hard part is to prove this theorem for compact manifolds. And again, if you're a little bit familiar with these methods of Gromov, you know that you typically go on extending your structure. So first of all, you give yourself a handle decomposition, so a Morse function for your manifold, for your closed manifold. You get the corresponding handle decomposition, and you keep on extending the structure as you attach handles. And the difference between a non-compact and a compact manifold is when you have a non-compact manifold, there is no handle of top dimension. So there is no ball that you attach along its boundary, along the sphere, that you have to glue to close up the manifold. So Gromov knew how to extend contact structures for manifolds that don't have like top dimensional balls. And the work of Borman, Eliashberg, and Murphy was to show essentially how a compact structure defined on the sphere extends to a contact structure defined on the ball. So this is really the theorem, to go from the sphere with a germ of contact structure. So this is a, let's say, an open neighborhood of the sphere gives you or allows you to so any contact structure defined on the sphere extends in a very complicated way to a contact structure in the ball. I mean S to N. Thank you very much. No, I don't mean S to N. Yes, you're right. I mean that. Thank you, sorry. Sorry. It's a problem of... So I'll say a little bit more of the kind of contact structures that emerge in this theorem, but for that I really need to continue with a bit more of theory. Also to make precise the theorem. So for that, let me discuss very briefly isotopies. contact homomorphisms and gray stability. And essentially, if one can summarize all, or at least the part that concerns isotopies, well, almost all here in, let's say, Moser's trick in contact geometry. So this is really about the version of Moser's trick that we have for this kind of geometry. So again, very briefly. So suppose that we have a manifold which is almost contact. That theorem tells us automatically that we do have contact structures. So we may look at the space of contact structures on the given manifold. So we can assume that it's non-empty. So contact structures on M. Right, so let me make a first observation. So I'm going to look at contact structures inside the set of hyperplane distributions of my given manifold, right? Remember that those were the sections of the bundle of contact elements. I simply want to do that to put a reasonable topology on these contact structures. Now, one first observation, which is analogous to the one that we know it happens for symplectic geometry, is that this is an open subset of the set of hyperplane distributions in the contact manifold. This is because the contact condition is open. You can, remember, you can rephrase it as alpha wedge d alpha to the nth power being a volume form. That's an open condition, right? So this is an open subset. And, well, of course, in principle, when you study any kind of geometry, you are interested in contact structures originally up to diffeomorphism. So what can we say about contact structures up to diffeomorphism? So let me introduce a definition. So a couple of equivalence relations on contact structures. So I'll say that two contact structures, psi and psi prime on M, are contact homotopic. If there exists a path of contact structures that joins them. I'm not sure how much. So again, if this is an open component, so is this, if this is a connected component of the open set of contact structures inside hyperplane distributions, this equivalence relation basically picks connected components. I want psi, psi prime, and then I want them to belong to the same connected component in that sense. So that's what one is looking at. There's a second definition. I'm going to say that these two contact structures are contact isotopic. If there exists an isotopy such that the pullback the pullback by the time one diffeomorphism of psi prime is psi. And of course, the second condition implies the first, because each time that I have an isotopy, I can produce a one-parameter family given simply by pushing, using the isotopy, the first contact structure. So essentially, this kind of equivalent relation is stronger because the curves that I'm interested in, these curves are constructed using isotopies. Of course, why is there relevant the second definition for the kind of problem we're interested in? Because we want to study contact structures up to diffeomorphism. The only problem, the catch here, is that when you study diffeomorphisms are complicated to grasp. Now, really, what you want is infinitesimal methods to be able to handle with diffeomorphisms. So that's why you only work with diffeomorphisms in the connected component identity, because then you can use the one-parameter family of vector fields to pinpoint them. So that's essentially when this problem is not that reasonable. This one is much more reasonable. And the good thing about Moser's methods in contact manifolds is that when M is a compact manifold, the first condition implies the second. Whenever we have a path of contact structures, that path can be substituted by a second path which comes from isotopy. Okay, so let me write that. So this is a theorem of Gray that says that for M compact, psi prime contact homotopic imply contact isotopic. Hence, if we want to study contact structures up to isotopy, it's the same thing as studying connected components of the set of contact structures on our given compact manifold. That's the advantage. And let me also draw a corollary, so known as Gray's stability. It's actually, well, so M compact, Xi contact structure on M, then there exists an open neighborhood of this contact structure inside the space of hyperplane distributions, such that for all distribution that you find in this open subset, D is contact, and moreover, D is contact isotopic to the given distribution, right? So this is our rigidity result. If you have a contact structure on a closed manifold, then all hyperplane distributions or nearby hyperplane distributions are equivalent to the given one. So you have a global change of coordinates, a diffeomorphism that takes the nearby hyperplane distribution into the given one. All right. So I'd like, to maybe go back to this theorem and then say something else. So more precisely, so this theorem is much more things. In particular, it says the following thing. If you look at the space of contact structures on M, I put here an superindex OT that stands for over-twisted. This is some kind of contact structure. Then the inclusion of this kind of structures on the subset of almost contact hyperplane distribution is a homotopy equivalence. So in particular, if you think at the level of connected components, each time that you have a connected component here, that connected component contains up to isotopy a unique over-twisted contact structure. So you see, the problem of discussing this particular kind of contact structures becomes entirely homotopic. You have your manifold, you look at the space of almost contact structures, you look at the connected components, each connected component essentially gives you just one of these contact structures up to diffeomorphism, right? So what is this over-twisted contact structures? I'm not even able to give you the definition in higher dimensions. I can give you the definition of three-dimensional over-twisted contact structures. So, and not even the precise definition. So, when a contact structure on a three-dimensional closed, let's say, yes, closed manifold is over-twisted, well, when you're able to embed the disk, again, I'm not being entirely precise with the definition, but so this is a surface, so you can intersect this surface with the contact distribution, and generically you're going to see here a line field. Now, the line field that you're going to see is as follows. So you're going to see a tangency point here. You're going to see also tangency points along the boundary, so the whole boundary is going to be an integral curve. And the other integral curves, basically, they are going to spiral around the disk. So this is the kind of, no, that's the definition. An over-twisted contact structure on a three-dimensional manifold is a contact structure that admits an embedding of the disk that has a very specific germ of contact structure that has this appearance. Now, well, in general, there's a different notion of over-twisted disk of dimension 2n, and the definition is similar. Let me tell you that, of course, this condition is global. I mean, locally, if you apply, as we shall see, if we apply Gray's theorem and produce a Darboux theorem, we won't see this kind of objects. And again, for those of you who are used to foliation theory, what is the analog of an over-twisted disk? So the analog of an over-twisted disk in the world of foliation by surfaces on three manifolds are rib components. So if you have a foliation by surfaces on a three-dimensional manifold, there's a very classical way of producing a new foliation by requiring the existence of a transverse cycle. And of course, the existence of such cycle is something which is global. That's not a local property, so it has to be a closed cycle. Once you have a closed cycle, what you can do is basically turbulize the foliation along the cycle. And that's going to produce a new foliation which is going to have a rib component here and is going to do something different. Well, if you perform this process in the contact world, what you do is, given a contact three manifold, given a transverse cycle, you can produce a new contact structure that contains an over-twisted disk. So you can always spoil any given three-dimensional contact structure into an over-twisted one. Now, what is the advantage of spoiling your contact structure by putting over-twisted disk? That this theorem tells you that these guys are incredibly flexible, that basically they abide by homotopic methods. So you do something that makes the contact structure look worse, but you have complete homotopic control over them. So let me also tell you that in three-dimensional contact geometry, the contact structures which are not over-twisted are called tight. And in general, theorems for tight contact structure, apart from that monster theorems, are much more beautiful and much more interesting. So I'll show you examples of structures, three-dimensional contact structures, which are tight. These are the ones that appear in very, very natural construction. So, okay, let me just continue talking about the Gray's theorem very briefly. Because you see, I mean, so let me just fix my contact structure with a global one form. And let me choose an isotopy or any isotopy with the property that the isotopy leaves the contact structure stationary. So that contact distribution is a fixed point set for 5T. Now, write this condition at the level of one form. So this basically means that condition. Typically, you want to extract some infinitesimal conditions. So if this isotopy is associated to the one-parameter family of vector fields xt, then upon differentiation, you will get the following identity. where here, I mean, you have to make a manipulation. You have to use also this equation on this right-hand side. So in particular, if your isotopy leaves the contact structure stationary, the infinitesimal condition that you get is here. And that's the infinitesimal condition that you essentially use to define contact vector fields. So definition, given a contact manifold, M curd the alpha. So a vector field is called contact if it scales the one form upon taking the derivative. And of course, if you can integrate this vector field into an isotopy, what you will get is an isotopy that fixes the contact distribution. So among contact vector fields, let me introduce the Rip vector field. So the Rip vector field for the contact one form alpha, R alpha, is the vector field characterized by the following. So the kernel of these two forms is one-dimensional because it's a symplectic form in the hyperplane distribution. So you basically take a vector field in the kernel. So this is a coorientable distribution. And what you do now is you normalize this vector field, and the normalization condition is simply obrigado. I completely forgot. And so that's the Rip vector field. And I mean, these conditions really imply the much more stronger condition here. That, of course, imply that your Rip vector field, in particular, is a contact vector field, right? Now, I don't want to erase that one, just in case. So why Rip vector fields are important? Well, because, I mean, you can do dynamical systems on a given manifold, but it turns out that when you study the dynamical system associated to a Rip vector field, problems such as trying to find closed orbits are much more, let's say, you have much more tools than for an arbitrary vector field. So because at contact dynamics, looks in particular to dynamical properties of Rip vector fields. For example, closed trajectories. And linked to that question, there's a very famous conjecture which has been proven in many cases, the Weinstein conjecture, that asserts the existence of closed trajectories for contact forms on closed manifolds. So again, you should ask the experts in dynamics in the audience for an update on this conjecture. Well, so my purpose with contact and Rip vector field is much more humble. So I want to make the following remark on both on the contact and on the Rip condition. So it's a very basic observation that there is a one-to-one correspondence between smooth functions and Rip vector fields for a co-oriented contact structure. Simply, you choose a function and you associate to them the Rip vector field of the scaled contact one form. So that's a one-to-one correspondence. And what you can do now is, you see, for any vector field on your manifold, what you can do is write the vector field as a multiple of the Rip vector field plus another component which is tangent to the contact distribution. So it's basically splitting a given vector field. So this is tangent to psi. And simply use that splitting and run again the contact condition that you have over there. And you'll basically see that the contact condition tells you that the vector field X is contact if and only if minus the exterior derivative of H plus the contraction of d alpha with Z is a multiple of alpha. In particular, it tells you that given any function H, you can solve uniquely this equation and produce the corresponding contact vector field, which is the so-called contact Hamiltonian. So this is the contact Hamiltonian of the function H. And now you can do several things with that contact Hamiltonians. So let me, in fact, before going to Hamiltonians, let me derive some consequences of that equation. So that equation tells you in particular that you never have contact vector fields which are everywhere tangent to the constant to the contact distribution. That's absolutely impossible because you cannot solve. Well, the only one is the so the only one is a zero vector field. So that's the first condition. The second condition. So we have no contact vector fields tangent to the contact distribution. Second condition, given a contact vector field, you can ask yourself when this contact vector field is the real vector field for some contact one form, and that is the case. So a contact vector field is the real of some multiple of the contact vector field of the contact one form if and only if this guy is everywhere transverse to the distribution. So real vector fields are the contact vector fields which are everywhere transverse to the contact distribution. And on the contrary, guys everywhere tangent to the constant distribution can never be contact vector fields. Now, what can you do with contact Hamiltonians? So again, remember your lectures on symplectic geometry, and you know that each time that you can use the Hamiltonian vector fields in symplectic geometry to produce a bracket on functions, the so-called Poisson bracket. So here you can do the same thing. So formally, given a function, you associate a vector field. So you can define the bracket of the functions h and g as dj applied to the Hamiltonian vector field of h. And you can study the properties of this operation. And what you find out is that unlike in the symplectic case, well, you have a bracket here which, well, it's a Lie algebra. It's actually a local Lie algebra, so it decreases the support. But it's not true that it verifies some sort of Leibniz rule. So in any case, that brings a different viewpoint on contact structures. So you can study contact structures from the viewpoint of local Lie algebra structures on the sheaf of functions of your given manifold. So these are the same thing. So contact structures. Let me say contact forms, to be more precise, on M are the same thing as local Lie algebra structures on C infinity of M, more generally on the sheaf of functions. Now, whenever you have these kind of brackets, I mean, this is a structure that you typically study on functions on M. You can also look at functions which have coefficients on a local system. And in particular, you can also recover non-coorientable contact structures just putting a local Lie algebra bracket on sections of the corresponding orientation bundle. For me, looking at contact structure from the viewpoint of local Lie algebras is especially interesting when you're doing holomorphic contact geometry for the following reason. So this is interesting for holomorphic contact structures. Because you see, I mean, how would you define a holomorphic one form? So you have your complex manifold. And the way to define contact one forms is basically taking a holomorphic section of T star 1, 0. Yes, holomorphic one form, which is nowhere vanishing, and that satisfies the maximal non-integrability condition. Now, when X is, or in many situations, this holomorphic vector bundle won't have any global section. So it's actually non-reasonable even to look for this kind of one forms. But it may very well happen that if you tensor this guy with a line bundle, the line bundle of a divisor, then you may find sections here which satisfy the contact condition. So that would give you a theory of contact geometry with coefficients, and it's worth looking at it. Right? So that's the use of local coefficients, local systems of coefficients. Yeah, I want to finish the story about Gray's theorem. Yeah. So how do you prove Gray's theorem? So how do you apply Moser's method to build out of a path of contact structures an isotopy that produces the path, right? So that's a problem that you want to solve. Given a path, a one-parameter family of contact structures, you look for an isotopy that pulls back the path to the original one, right? And as usual, you'll write it using forms. Let's assume, again, coorientability. If it's not coorientable, we go to a double cover, solve the problem there, and then go back with an equivariant solution. So you want to solve this thing, and then when you differentiate, so you will have the corresponding infinitesimal condition. Now, when you apply Moser's method to symplectic manifolds, that infinitesimal condition has a unique solution, and that's the way you get the corresponding isotopy. When you try to look at the infinitesimal condition, that infinitesimal condition doesn't give you, in general, a unique solution. But if you do the following thing, if you require that these vector fields be tangent to the corresponding contact distribution, you get a unique solution. So there exists a unique one-parameter family of vector fields that is going to satisfy the corresponding infinitesimal equation, plus it's going to be tangent to these distributions. Now, why this is reasonable? I mean, this condition, of course, I mean, you can say, well, if I impose it, then I get the unique solution. But it's also reasonable in terms of this situation for contact vector fields. So you know that the contact vector fields for these guys are vector fields which are everywhere transverse to the corresponding contact distribution. So if you want to go from psi1 to psi0 in an optimal way, you shouldn't use transverse vector fields. You should go tangent to the distribution. So a fortiori, this is some sort of explanation for these algebraic tricks that gives you the Moser's theorem in contact geometry. Well, again, so the compactness assumption is used simply to produce out of a one-parameter family of vector fields the corresponding isotopy, which means that when you are, for example, in a local situation, you don't require that condition. In particular, this gives you Darboux theorems around points, around Legendrians, around isotropic submanifolds with some additional linear information. So what you can get is Darboux-type theorems. So again, as you might expect, so there are no local invariants on contact geometry. We saw it by hand in the three-dimensional case. You can prove it in any dimension. All right, so I have something like 15 minutes to discuss more close relations between contact geometry and symplectic geometry. All right, so let me introduce what is the symplectization of a given manifold with a contact one form. So given M alpha contact, its symplectization is the following manifold. So you cross M with the reals, and you put the following exact 2 form, which is the exterior derivative of et times alpha, when of course I'm not writing pullbacks to the for the corresponding factor, so I'm using here the t variable. And you right away check that the contact condition on alpha implies that this is a symplectic form, right? So all right, so how we do go back from the symplectization to the contact manifold, right? What is the opposite process? So that process uses Liouville vector fields. So if I have a symplectic manifold, remember that a vector field is Liouville if it scales exponentially the symplectic form. So infinitesimally, it means that condition. And if on a symplectic manifold you have a Liouville vector field, and on top of that, you have a hypersurface which is transverse to that Liouville vector field. What you can do is induce a contact form on that hypersurface in the following way. So you define alpha, which is going to be a contact form on N, to be the result of contracting the symplectic form omega with the Liouville vector field, and then restrict this to your hypersurface. So one simple observation. So what is the kernel of this one form at every point of the symplectic manifold? So the kernel of this one form is the symplectic annihilator of the vector field X. Now, because the vector field at the points of the hypersurface N is transverse, it means that this hyperplane distribution, the annihilator of X, is everywhere transverse to the tangent bundle of N, which means that it induces a hyperplane distribution on N. Now, for that hyperplane distribution, the contact condition is basically the symplectic condition along N that you can check right away. All right, so one more example. So if you are now in the symplectization of the contact manifold M, you can check that ddt is Liouville, and of course M cross 0, for example, actually any of these copies, is a hypersurface transverse to this guy, which means that if you apply that process, you're going to cook a contact form on M, which is going to be, of course, the original contact form alpha. So this is the way of, starting with a contact manifold, going to the symplectization, and going back to the contact manifold. But it does work, this going back, it does work in more general situations. Now, this is telling you, essentially, that there is a one-to-one correspondence between doing contact geometry or contact geometry on M is the same thing as doing symplectic geometry on the symplectization. But it can't be any symplectic geometry. You have to recall that the symplectic geometry has to be compatible with this Liouville vector field. So it's so-called homogeneous symplectic geometry. Now, this is, you shouldn't think that then, well, after all, contact geometry is just a subset of symplectic geometry. Well, this is not quite the case, because if you want to do contact topology, in fact, on compact manifolds, when you do the symplectization, you get to a non-compact manifold. So on a non-compact manifold, symplectic methods compatible with the Liouville vector fields in general do not exist. So you can basically, you cannot solve any problem on contact topology by solving it on the symplectization. However, this symplectization is extremely useful for some sort of questions that you want to tackle. For instance, I think that Vinny will discuss a version of contact homology on Friday that uses pseudo-holomorphic curves in the symplectization of a contact manifold. So that's one nice use of the symplectization of a contact manifold. Right? So more examples. So consider the cotangent bundle of any given manifold with the standard symplectic form, the exterior derivative of the Liouville symplectic form. Yes. And you observe the following thing. The Euler vector field is Liouville. Right? So it means that if I take any hypersurface inside of the cotangent bundle, which is transverse to the Euler vector field, I'm going to induce a contact structure on that. In particular, if I take the sphere bundle associated to any metric. Right? So that's another way of recovering a contact form on the sphere bundles associated to. So for example, take G, a metric, on T star of M, pick the corresponding sphere bundle, and then run that construction. And when you run that construction, you end up with the restriction of the Liouville 1 form to the sphere bundle. So again, that doesn't give you anything new. However, this combines with Gray's theorem essentially tells you that all these contact structures are the same. So why? Because, I mean, imagine that you choose a different Riemannian metric, a different representation of the sphere bundle. So you have two Riemannian metrics, and you can join them by a path. So that will give you a path of hypersurfaces. You can use the trajectories of the Euler vector fields to identify all the sphere bundles with a given one. And in that way, you pull back all contact forms to the contact form on G0. And there you have a one-parameter family of contact forms which, modulo compactness assumption, by Gray's theorem, they are essentially the same up to isotopy. Right? So again, does not depend on G up to isotopy plus the conditions to be able to have that isotopy. One more example. So take the unit sphere in odd dimensions. And here with the standard symplectic form. And observe once more that one half of the Euler vector field is Liouville. Right? Now the unit sphere is tangent to the Euler, is transverse to the Euler vector field. So that means that you have a way of inducing, let's call a standard contact one form on the sphere. So that's one of the ways of putting a nice contact structure on the sphere. I erased the theorem. All right, so let me tell you that this is an example of a fillable contact structure. Or I would say here a strongly fillable contact structure. So how do you define in general a fillable contact structure? So you have your contact manifold, which is supposed to be the curve. So this is M psi. And this contact manifold, it should bound a symplectic manifold, and there should be some sort of compatibility between omega and alpha. One of the possible compatibility conditions is precisely having an Euler vector field that points outwards, such that you cook alpha using the previous process as the contraction of the Liouville vector field with the two form, and then the restriction to the boundary of X, which is M. So that would be a strong symplectic fillability. There are weaker notions of symplectic fillability. And of course, the sphere is one example. Now, why these kind of symplectic manifolds are relevant? Well, because if you go back to the theorem of Borman, Eliashberg, and Murphy that produces over-twisted contact structures, an over-twisted contact structure is never symplectically fillable. So that kind of contact structures are not the ones that came from that theorem. And these actually are much more interesting because, for example, you can apply methods of holomorphic curves to this symplectic filling to tell things about the contact boundary, which in general you cannot do for an arbitrary, or you can do for an arbitrary contact manifold. It's just that when you work with the symplectization, you have two boundary components, and, well, the situation is much more complicated. You get less things. So so let me actually put something here. So another example. So how do you get this kind of a strongly fillable contact structure? So very often, so very much as you use Keller geometry as a source of inspiration for symplectic geometry, there's another part of complex geometry that you can use to produce contact manifolds, in particular to produce this kind of contact manifolds which are filled by symplectic manifolds. So specifically, if you start with a Keller manifold, so this is a Keller manifold, and, well, you can ask the closed-to form to be exacting cohomology, but because you are in the complex setting, you can ask for a different kind of exactness. So you can actually require the existence of a global Keller potential for this Keller form. So assume that there exists H, a Keller potential. So this would be Stein manifold, or Stein domain, to be more precise, if I'm with potential. So this H, this means simply this equation. And in these Keller manifolds with potential, it turns out that, well, if you take X to be the gradient of the Keller metric, this is a Liouville vector field, which means that if you have here the manifold xj, and you take a regular value of the function h, then this is a hypersurface which is transversed to that Liouville vector field. Hence, you produce here a contact structure. So this is a CR structure of a strictly convex type. So what I want to tell you is that you can use Keller geometry, classical Keller geometry, to produce examples of nice contact manifolds, right? Last example of a construction in Keller geometry, more generally in symplectic geometry, that out of a symplectic manifold produces a new contact manifold. And that's going to be basically the would-be one construction. So, and with that, I'll finish the introduction. So again, there's one very clear relation between symplectic and contact geometry that goes from contact to symplectic using symplectization, and then going back using a hypersurface and a Liouville vector field. So that goes back and forth. There's a second way of going from symplectic to contact, which is this classical would-be one construction. You can think that you start, well, it has symplectic, doesn't have to be Keller. So take X omega asymplectic manifold with the assumption that your cohomology class is in the image of the integral cohomology. So in such situation, you know that you have the pre-quantum line bundle. So this is a line bundle whose first Chern class is precisely this guy, but even more, this line bundle is Hermitian. So there is a Hermitian inner product on the one-dimensional complex fibers. And on top of that, you can choose a connection form compatible with the Hermitian structure such that its curvature, well, up to normalization, so its curvature is the given symplectic form. Now, how do you get a contact manifold there? Well, I mean, you have the Hermitian metric, so you can go to the corresponding sphere bundle of L for the metric. So that's a hypersurface. The condition that the connection be compatible with the Hermitian structure, you can reverse it in geometric terms. This is equivalent to saying that if you look at the connection as a distribution by complex hyperplanes, these hyperplanes, they have to be tangent to the sphere bundles of L. So these are vectors in L such that HVV equal to 1. In general, if you fix any value here, you get the corresponding sphere bundle of that radius. And then that distribution by complex hyperplanes is going to be tangent to this hypersurface, which means that as real vector spaces, they will produce for you a hyperplane distribution here. So this is this with the horizontal space of the connection. This is a hyperplane distribution. Now, essentially, whether this distribution is integrable or not is given by the curvature. If the curvature is maximally non-degenerate, if the curvature is symplectic, then this is contact. Otherwise, it is not. So this is a hyperplane distribution, which is contact because the curvature is symplectic, is non-degenerate. So you see, perhaps one can also say that these, as contact manifolds, these are very particular because what you can do is, you can essentially, there is a Reed vector field. So here, you can basically write the connection one form here on this sphere bundle, and this connection one form is a one form, is a usual one form on the sphere bundle. And it's a contact one form. And if you look at the Reed vector field of this contact one form, this is the infinitesimal generator of the S1 action. So all the Reed orbits are closed. They are the fibers of this. So has orbits the S1 fibers. So I have 1 minute, so perhaps let me enlarge this kind of a structure. So if you have a Stein manifold, or if you have a Stein domain, the boundary is a very nice symplectic manifold. You can also get symplectic manifolds in a similar way, not using Stein manifolds. You can use Stein varieties. They don't have to be smooth. And there's a very classical source of those examples. For example, for instance, if you take a function that has an isolated complex singularity at the origin. So more generally, you can use Stein spaces. And the classical example is in Cn, take, for example, so this gives you, this function has an isolated singularity at the origin. So what you can do is take the inverse image of the origin, and what you will see is something like that. So again, 0 is not a regular value, so that's not a complex hypersurface. There is a singularity here, so maybe we do the picture like this. But still, if you take here the intersection with the sphere of a small radius, so that's a classical thing that people do when they study this kind of singularities, this is a construction by Milner, for example. If you take that intersection here, then what you get here is a contact structure. because essentially this guy here is a Stein domain if you put as function h the square of the norm, right? So again, this is a very natural, very nice source of examples in contact geometry, links of isolated complex singularities. Okay, I think I should stop here.